Welcome back, students. Okay, we're going to jump right into this complete revision explainer of KSSM Form 2 Mathematics, Chapter 9. Today, we're breaking down the exact logical steps behind speed and acceleration so you can absolutely crush your exams and score full marks. We're going to unpack the math together and make it super straightforward. Let's get into it.
Here's our quick roadmap for today's explainer. We'll kick things off with basic speed concepts, move right into uniform and average speed, and then tackle acceleration and deceleration. After that, we'll build up to those famously tricky unit conversion questions, and finally wrap the whole thing up with a chapter summary and some must-know exam tips.
All right, Section 1. Let's start with the big question. What exactly is speed? At its core, speed is simply a rate, and to find it, we just divide the distance moved by the time taken. Think about it like this. If Ida is walking to a shop and she covers 100 meters in 5 minutes, we just divide 100 by 5. Boom! That gives her a speed of 20 meters per minute. It literally just means Ida is walking exactly 20 meters every single minute. Now, this is a perfect real-world example of the formula in action. Take these two sprinters, Kyrol and Bodrol. They're running the 100-meter dash. Kyrol finishes in 10.18 seconds, and Bodrol comes in right behind him at 10.25 seconds. Since Kyrol takes slightly less time to cover that exact same 100-meter distance, basic logic tells us his speed has to be higher, right? And the math absolutely backs that up. 100 divided by 10.18 gives Kyrol a winning speed of 9.82 meters per second, just edging out Bodrol's 9.76. So that's a quick sprint, but Section 2 builds on this. What happens when speeds take place over a longer journey with variations? Let's talk uniform and average speed.
There's a massive difference between moving at a uniform speed versus a non-uniform speed. Imagine a marble, marble A, rolling along at a perfectly steady pace. It covers the exact same distance in equal intervals of time. That's uniform speed. But marble B? It's shifting gears, constantly changing paces, covering totally unequal distances in those same time intervals. That's non-uniform speed.
Let's test this out with a practical question. Picture Fari driving a trailer, and his journey is split into two very different legs. For the first 2 hours, he drives 170 kilometers. But for the next 4 hours, he only drives 190 kilometers. So, think logically for a second. Did his speed stay uniform? Let's crunch the numbers step by step. For the first 2 hours, 170 divided by 2 gives him a pretty solid initial speed of 85 kilometers per hour. But leg 2, 190 divided by 4 means his speed drastically dropped to just 47.5 kilometers per hour. Since 85 obviously doesn't equal 47.5, we can say for sure his speed was non-uniform. So what's the game plan for journeys that constantly change speeds? Say Amir starts cycling from Satabek at 9 a.m., stops at a pizzeria to eat, and finally rolls into town at 12:15 p.m. For situations like this, we have to use the average speed formula, which relies entirely on taking the total distance and dividing it by the total time. To figure out Amir's average speed, we just add his two journey legs, 10 kilometers and 25 kilometers, giving us a total distance of 35 kilometers. His total time from 9 a.m. to 12:15 p.m. is 3 hours and 15 minutes, or 3.25 hours. Divide that 35 kilometers by 3.25 hours, and Amir's average speed comes out to exactly 10.77 kilometers per hour.
Okay, moving into Section 3, Subtopic 9.2. What mathematically happens when you're not just moving, but actively increasing your speed?
That brings us to acceleration. Acceleration is literally all about change. The formula is simply your change in speed divided by the time it took. For instance, if you're racing on a bike at a steady 10 meters per second, and then you pedal hard, bumping your speed up to 16 meters per second over the next 2 seconds, you are accelerating. Here's how we calculate it. First, find that change in speed. 16 minus 10 leaves us with 6 meters per second. Then, we divide that 6 by the 2 seconds it took. That gives us an acceleration of 3 meters per second, which you'll usually see written as 3 meters per second squared. It means every single second you're pedaling, your speed increases by another 3 meters per second.
But hey, what speeds up must eventually slow down, right? Let's check out Section 4 and explore the exact opposite of acceleration.
Imagine a motorcycle cruising at 20 meters per second. Suddenly, the rider hits the brakes, slowing down steadily until they come to a complete stop 4 seconds later. To find the change in speed here, we always subtract the initial speed from the final speed. So, 0 minus 20 gives us a negative 20. Divide that negative 20 by the 4 seconds it took to stop, and we get an acceleration of negative 5 meters per second squared.
Now pay close attention here, because this is an absolute classic exam trap. Deceleration simply means a decrease in speed. If your math gives you a negative acceleration of, say, negative 5, that translates directly to a deceleration of 5 meters per second squared. Don't write a deceleration of negative 5. The word deceleration already does the job of telling the examiner it's a negative change.
All right, Section 5. Time to tackle the part of Chapter 9 that honestly trips up so many students: unit conversions. Let's make this easy. When you need to convert kilometers per hour into meters per second, just remember that speed is a fraction, distance on top, time on the bottom. So systematically convert the top by multiplying the kilometers by 1,000 to get your meters. Then deal with the bottom. Convert hours to minutes by multiplying by 60, and then to seconds by multiplying by 60 again, which is 3,600 seconds. Finally, just divide your new total meters by your new total seconds.
Mastering these conversions is a total game changer for complex word problems. Take Ronnie traveling to a cultural festival. Going there, she accelerated at 24 kilometers per hour squared. On the way back, she made the trip in 40% less time, which works out to an acceleration of 40 kilometers per hour squared. By keeping our units organized and converting carefully, we can easily find the difference between her two trips, which is exactly 16 kilometers per hour squared. No panic necessary.
Well, we've covered a ton of ground today. For our final section, let's pull all of this into a quick, punchy study guide you can use right before your test.
Seriously, take a mental screenshot right now. These are your golden rules. Remember your core formulas. Speed is distance over time. Acceleration is the change in speed over time. Average speed always needs the total distance and the total time. For the exam, always check your units first. Remember that a negative acceleration is just deceleration. And please, show your work step by step. Even if you did it in your head, the examiner needs to see it to give you those full marks.
So, before we wrap up, I've got a challenge for you to bring this math into the real world. Next time you're heading to school in a car or on a motorcycle, just watch the speedometer for a minute. Ask yourself, is this math happening right in front of me? Are we holding a uniform speed? Are we accelerating, or are we safely decelerating? Keep observing, keep practicing, and good luck with your revision. You've got this.